Hello, my name is David Bowie. I am a mathematics teacher at Lewiston High School in Lewiston, Maine. This GeoGebra video tutorial is sponsored by MLTI, the Maine Learning Technology Initiative. This is one of MLTI's programs for providing professional development to Maine teachers. In this video, the third in the statistics series, we're going to look at correlation. We're going to use the GeoGebra spreadsheet and graphing tools to find the correlation coefficient to plot regression equation, curves, and straight lines. Today, secondary students are expected to have an understanding of several areas of statistics. One of those is correlation. GeoGebra offers several ways to explore and explain correlation. Let's take an example of hours spent studying for a test compared to the student's test score. We'll take that data from an Excel spreadsheet and simply paste it in. Of course, we could type the data in directly if we wanted to. So we have study hours and we have test time. In GeoGebra, we'll take the data and create points so that each value in column A will be an X, each value in column B will be the corresponding Y. We could create lists of each individual column, but in this case, having points will be more useful for our purposes. Using the right click on a two-button mouse or using control click, we can create a list of points. That list appears over in our algebra window, and we'll change that to rename it to points, just for simplicity. Now at first glance it appears that nothing happened in the graphics window, but actually it did. As soon as the list was created, GeoGebra plotted those points. They're simply off the viewing area right now. So we will move our axes. We'll have to reduce the y-axis to bring our values into view. Okay, there are our points are starting to come into view. We also need to reduce the x-axis just a little. The largest value we had was 8. Now students would already be seeing a fairly strong linear correlation between the x and y values of our data. GeoGebra allows us to go a bit further from that. We might want to ask the students first what they would perceive to be the correlation coefficient, if that's something they've looked at this point. They should be guessing a fairly strong one, so getting fairly upwards towards a 1, perhaps a 0.8, 0.9, somewhere in there would be a pretty good guess with just the points to look at this time. Now we'll calculate the coefficient. We can do that in a couple places, but let's just go to the input bar and we'll simply type in the command for correlation coefficient. And we've gotten through 4 letters, brings it up for us. We're now ready to enter the data we want. We have a choice here. When you're using correlation coefficient, you can put in the list of x and list of y values, or in our case, since we've created them as a list of points, we simply put in the list of points, and that is as simple as typing the word points, hit enter, and the value A showing up on our algebra window is the correlation coefficient. And we could rename that, and we will. Let's call that R and make it a little bit more meaningful and more consistent with the Pearson R value. GeoGebra also has the capability of putting in our line of best fit or our regression line. The command for that is fitLine. There is also a tool that will do that we'll look at in a later example. The fit line we want is for the same set of points, so we'll simply type in the word points, and there is our fit line. Notice that the equation appears in the algebra window. It's not in the format we are typically used to seeing when we're working with regression lines, but we can easily click on it or control click on it, and we can change it to either the equation y equals mx plus b form or parametric form. This form we're probably most accustomed to is y equals mx plus b. So there's the equation of our regression line, y equals 7.35x plus 34.62. This is a good time to reinforce the concept of correlation and the usefulness of the regression line. Ask students to take a look at the line and estimate what score would a student receive if the student had studied for 3 hours. We don't have that particular number of hours in our list. Looking at the line, they should be able to estimate somewhere in the vicinity of 60 hours. Let's see what the regression line would give us for a result. We'll go down to our input bar and we'll type in P equals, or any label you want for your point. The x-coordinate is going to be 3, as in 3 hours. The y-coordinate will be generated by the equation of the regression line itself. So that will be 7.35 times the 3 plus 34.62. And we'll close our parentheses. There is an option available. If we right-click on the equation, we have a copy to input bar capability that would be useful on more complicated equations. But for a simple equation, it's probably just as easy to type in the equation values as you go along. As soon as we hit enter, our point does show up on the line about where we expected it, and if we look at the point in the algebra window, we see that the y-coordinate generated is 56.67. So we would probably say that 3 hours would result in a predicted score of 57. Students are often confused in working with regression because they don't understand the difference between the slope of the regression line and the correlation coefficient. The dynamic capabilities of GeoGebra provide us a powerful way to explore those two ideas. In our screen right now, we've eliminated the point P that we used a few moments ago as a test point, and our original 13 points are still in view. Using the Move tool, we can demonstrate the impact of moving any of our points. Now this will change the values to some rather unfeasible values as far as the original data was concerned, but they'll demonstrate the idea. We'll take a point near the center of the line and we'll drag it. Now we see a very small impact on the line itself. It's pulling it slowly, but if we move it straight away at a perpendicular angle, it does not impact the slope very much at all. We'll return that line to its original position. If we take a point on an end, we can explore the ideas of influence and see how a line that's far out on an extreme, pulling that just slightly, very quickly moves that line much more than the point near the middle did. We'll put it back to its original location. At the same time, we can take a look at what's happening to our correlation. It's been at 0.92, strong correlation. We can grab a point, we'll take this point, and noticing that our slope is 7.35, let's move this point considerably. In fact, let's move it way down to the other end here, and we'll bring it back to about 7.35. That's quite close, but with making very little change in the slope, we've had a dramatic change from 0.92 down to 0.79 in the correlation. So the two are connected to each other, but they are not the same measure at all. GeoGebra allows us a very powerful way to demonstrate this relationship within the concept of correlation. As our last example in statistics and correlation, let's take a look at a more advanced correlation. We have a set of data already in place here. It is the shutter speeds and f-stops for a camera. On first observation, we notice that as the shutter speed goes up, so does the f-stop. So perhaps there is a linear correlation there. The first step we might want to take, if we don't want to look any deeper yet, is to find that linear correlation if there is one. So let's start the same way we did before. We'll select all of our ordered pairs. Using either the right click or control click, we'll create a list of points. Now we do have some points appearing over here, but the scale needs to be adjusted considerably. The y-axis scale will bring these points down. We need to go large enough to pick up 32, and there's our 32, our last point. We need to move the x scale as well, and we have to move quite a bit here before we, okay. Now we're starting to see perhaps not a linear relationship. There's some curve in here, curvature. Okay, so let's see what a linear fit would look like. So we'll go to our fit line, and this will be for list 1. We didn't rename it this time. Well, there's our fit line, but it doesn't fit awfully well. Again, we can very easily now see that that is not a straight line. We have points below the line here, and in the middle they're all above. Definitely not a straight line fit. GeoGebra has other fit capabilities as well. Students looking at the data may realize that there is a connection here, and it may have to do with some kind of a power relationship. So we will use an alternate approach. Instead of a linear fit, we'll type in fit, but we'll use power instead. We again will type in the list 1, and when we hit enter, GeoGebra draws the equation that of not a line this time, but over in our algebra window we see the function f of x equals 86.707 times x raised to the 0.497 power. What we have here, and a fairly close fit at this point, is a power fit, or a power function. The number 0.497 is very close to 0.5, or in other words, a square root. So we may want to do a test here. Let's go back to our input line. What if we type in an equation that's close to that, but in terms of square root? See if students can come up with an alternate way of writing it that would be more familiar to them, perhaps. Let's use the function g of x. Now our 86.7, let's just round that off to an 87. We could even go to 90 if we wanted. And we want the square root of x. So it's 87 times the square root of x. If we've done this correctly, our equation should match very closely to the existing function that we already have on display. Let's see. In fact, it is so close that all that happened was we got a little bit thicker line. You can't even see the difference between the two. If we choose our function that we just created, okay, we took it away, put it back. Very close match. In addition to the power function, GeoGebra can support exponential, logarithmic, logistic, polynomial, and sine curves as models for fitting data to. This concludes our look at examples for using GeoGebra in connection with statistics, and in this case we've been looking at the correlation, both linear and in this last case a power fit.